Evening. This class, I'll be looking at the correction for the assignment on chemical equilibrium. And without taking much time, start question number one. Question number one, hydrogen chloride undergoes a reversible reaction with oxygen. In this question, you can see that we have 4 mole of hydrogen chloride gas reacting with a mole of oxygen, both in the gaseous phase, reversibly to produce 2 mole of chlorine gas and then 2 mole of steam, also in the gaseous phase. The reaction is carried out at 400 degrees Celsius in the presence of a copper 2 chloride catalyst. Use the data in the table to calculate the overall enthalpy change for the reaction. Now, the copper 2 chloride is heterogeneous catalyst because the catalyst is in solid phase, while the reactant are both in the gaseous phase. So a catalyst that exists in another phase or state compared with the reactant, we call it heterogeneous catalyst. Whereas a catalyst that is in the same phase with the reactant, we call that one homogeneous catalyst. Therefore, in this reaction, an heterogeneous catalyst was used. The question number figure 1, use the data in the table to calculate the overall enthalpy change for the reaction. To do that, we must write the formula. Enthalpy change for the reaction is equal to the enthalpy change for the product minus the enthalpy change for the reactant. Having done that, we must consider as well the number of mole of the product and as well as the reactant. We have 2 mole of steam produced and then 4 mole of hydrogen chloride gas. Chlorine and oxygen are the value are assumed to be constant. So we are only given the mole of we are only given the enthalpy change for the formation of steam and hydrogen chloride gas. So now, the mole of the product, which is steam, the enthalpy change is minus 242 times 2. Minus 242 times 2. Why? Times 2, because that's the mole of steam. Then the mole of the reactant, which is HCl, is, the enthalpy change of formation of the reactant is minus 92. So minus times this minus will give me this plus. So I have a plus there. Then as I simply said 4 times 92 because I already said minus times minus. Since the enthalpy change for the formation of HCl is minus, so minus times this minus here will be plus over there. So that is plus, so I have plus here. So 4 times 92 will give me 368, while 2 times minus 242 will give me minus 484. Subtracting that, we're going to have minus 116 kilojoule per mole. The mark distribution, the first mark is on this, as your M1, and the second mark is on the answer M2. That is that for 2 marks. Mark figure 2, state the type of catalyst used in the reaction. Explain how a catalyst is able to increase the rate of reaction. In this question, you will see we have to state first and then also explain. State the catalyst used, heterogeneous catalyst. That's the type of catalyst. State this type of catalyst used. Heterogeneous catalyst. Explain your answer because it is in different state or phase to the reactant. So we have the mark distribution there for M1. This is your M1 and this is your M2. Okay. And then mark figure 3. The reaction exists in dynamic equilibrium. The reaction was repeated at 1000 degrees Celsius and the pressure remained the same. We are also to state it and state and explain the effect of the composition of the equilibrium mixture, the effect of the composition of the equilibrium mixture of the change in temperature. So at 1000 degrees Celsius, you discover that the product decomposes and then react. The product decomposes and react to form the reactant. So we have to state and explain. So state the effect on the composition of the equilibrium mixture. There will be more reactant than the product. That is the first one that we have to state there. Our explanation why the position of the equilibrium shifts, shifts to the left-hand side as delta H is exothermic or negative. So the product decomposes, and they react to form the reactant at 1000 degrees, because initially we have found that our delta H is minus 116 kilojoule per mole. So it's an exothermic change, and therefore increase in temperature will favor the backward reaction. So there is more of the reactant than product. That is our statement. Then we'll explain the position of equilibrium shift to the left-hand side because delta H is exothermic or negative, and then so the product at that temperature decomposes. They have to form the reactant. That's about that. Then figure 4. When 1.6 mole of hydrochloric hydrogen chloride gas are mixed in a sealed container is sealed with 0.500 moles of oxygen at 400 degrees Celsius, 0.600 moles of chlorine gas, and 0.600 moles of steam are formed. So we have the product given to us, and we also have the reactant. The total pressure inside the container is 1.50 to power minus 5 Pascal. Calculate the amount in mole of hydrogen chloride gas and oxygen gas in the equilibrium mixture. To tackle this kind of question, we need what we call the ICE table. The ICE table helps us to organize our reactant product in perspective. And so I stand for initial mole, and C stands for change in mole, and then we have the E. The E stands for equilibrium mole. So have E here as our equilibrium mole. Now, in order for us to understand the ICE table, we need to write the equation for the reaction. The equation for the reaction, as you can see here, is 4HCl and so on and so forth. So plus O2 to give us 2H2 and 2Cl2. Now, having done that, then we need to organize it in this way. Okay, so we have initial mole for HCl is 1.60, and we also have the initial mole of oxygen to be 0.5. And then initial moles for steam and chlorine is 0.0 because there was no reaction. Immediately reaction starts, we have change in mole. Change in mole here for the reactant, because the reactant will be decreasing the decrease in reactant will be according to the number of moles here. So 4. So we use X to represent the change in mole. So it will be, and then because it's decreasing, that way minus shows the decrease. Minus times 4x. X is a decrease, minus indicate there is a decrease. But the decrease goes with respect to the mole of the reactant. So for HCl is 4, so minus 4x there. So we have minus 4x there. And then for oxygen, there is 1 mole there. So simply the minus 1x or simply minus x. So that would be minus x there. And then going to, for the product will increase. So plus, okay? And the increase will be in at the rate of the mole of the product. We have 2 moles here. So it will be plus 2x. The change is in x as factor of x. Then to the mole plus 2x. For chlorine gas, also plus 2x. So plus for the product, okay, and then minus for the reactant. Minus indicates decrease in mole, and then plus indicates increase. And the increase is a factor of their mole. So X represents the increase product, and also X represents the decrease for the reactant, but it must be in the with respect to the number of mole of the reactant and product. Then equilibrium mole or equilibrium concentration, as the case may be. Okay, so here we are talking about mole, so it will be equilibrium mole, not equilibrium concentration. When you handle aqueous reaction, you will convert your mole to concentration. But now we are talking about gases, so we talk about equilibrium mole. So equilibrium mole here, you're simply going to add together. So here 0 plus 2x, we have 2x, and then 0 plus 2, we have 2x. We add together, that will be 0.5 minus x for oxygen. And if we add that for HCl, we have 1.4 minus 4x. That is that. But in the question, we discovered that 0.600 mole of chlorine and 0.600 mole of steam were formed. It means that there's 2x and 2x. So 2x, it means that 2x equals 0.6. 2x equals 0.6. From there, you know the value of x to be 0.3. So, having done that, we have to find the mole of HCl. And what it means is that all of 1.6 minus 4x. Since we know 4x, so I'm going to say 1.6 minus 4 times 0.3. If you do that math very well, you're going to have 0.4 as the mole of HCl at equilibrium. So we have 0.4. And for oxygen, 0.5 minus x. Since we know that x is 0.3, so 0.5 minus 3, we have 0.20. That represents the mole of the oxygen gas at equilibrium. So we have that. Calculate the mole fraction of chlorine, mole fraction of chlorine. So chlorine, and then the partial pressure of chlorine. The mole fraction of chlorine here, this one, will be the mole of chlorine is 0.6 over total mole. Total mole is 0.4 plus 0.2, 0.6, 0.6, we have 1.8. So the mole fraction will be 0.6 over 1.8, and that can be equals to 0.33 mole for that. Having done that, We are also asked to find the the partial pressure of chlorine. And to do that, partial pressure of chlorine will be 0.6 by 1.8 times the total pressure of the reaction. And that will give us 5.0 times 10 power 4 Pascal for that. So that has been done. And we are also told that in a separate experiment, an equilibrium reaction mixture was found to contain the four gases at the partial pressure shown below. So we have been given the partial pressure already. So there is no need for us to calculate the fraction of partial pressure. We simply add that one to the formula given. The formula is also given to us. You can see that Cambridge sometimes they are very, very nice guys, but not always nice. You have to be nice yourself. Okay. Looking at this, use the information and the expression given for Kp to calculate the value of Kp and state the unit for Kp. And so just putting the value and putting the value as it were, following the formula, we're going to find 1.0, 1.05 times 10 power minus 5. The Kp for the reaction, then the pressure, if you look at, I mean, the unit we have square here, we have square, and we have to power 4, 1. So we have P8 to power 4, but P8 to power 5, giving P8 to power minus 1. That is for the overall pressure. Then the reaction is repeated without a catalyst. Steady effect on this Kp. With catalyst or no catalyst, there will not be any effect. Kp is only affected by increase or decrease in temperature. So there is no effect. I know you got that one in your answer. Then we'll move on to question number 2. Magnesium oxide reacts reversibly with chlorine according to the following equation. MgO solid plus 2Cl gas reversibly to give us 2 MgCl2 solid plus nickel. Under certain conditions, a dynamic equilibrium is established. State 2 features of a reaction that's in dynamic equilibrium. Number 1, you got this one in your answer. Rate of forward reaction and backward reaction are equal. And number 2, once a reaction is in equilibrium, if the concentration of the reactant and product is a constant. So those are 2 fundamental properties of reaction that is in equilibrium. Other ones, when we meet in class, we'll talk about it. Let's go 2. The equilibrium constant Kp is given by the following expression. Kp equals to partial pressure of oxygen to power 1 and partial pressure of chlorine to power 2. At 1.00 times 10 power 5 Pascal and the 500 Kelvin, 70% of the initial amount of chlorine gas has reacted. 70% is the joker there. 70% of the reactant has been used up. We need to actually explain or interpret the 70% correctly. Calculate the Kp and state the unit. Here we will need the service of our ICE table, and here we have our ICE table here, first one here. Okay, so you will discover that magnesium oxide is solid, has no effect. Pressure has no effect on solid. When there are 2 solid, magnesium oxide and the magnesium chloride, they are out of the reaction. So we have 2 mole of chlorine reversibly forming a mole of oxygen gas. So our effort is focused on chlorine as a reactant as well as oxygen as the product. And then that was why they gave us the Kp is P partial pressure of over the partial pressure of chlorine 2. Now they're asking us find Kp. No reactant given. Whenever reactant is not given, we assume that 1 is a reactant. So therefore, the initial mole of chlorine, we can say here, it has 1. Initial mole of chlorine, that will be 1. And then oxygen, there is no reaction, so it's going to be 0. And then change in concentration, since there is 2 here, that will be minus 2x. And then for oxygen here, it's just a mole here, so that's plus x. Then equilibrium mole will be 1 minus 2x. So that one will be x. So you're going to add together, so 1 minus 2x, 0 plus x. Okay, so having done that, we'll now again look at the interpretation very well. 70% has been used. 70% has been used. So it means that if I start with 100, if I start with 100 mole, it means that I will have 70% being consumed. But here I'm starting with 1. So 1 mole. Starting with 1 mole means that 0.7, starting with 1.0 mole. Sorry about that. Starting with 1.0 mole means that minus 0.7 has been used, which is 70%. 0.7, 70%. That's 70%. So that's been used at 500 Kelvin, 70%, which means 0.7, but minus 0.7. And that will take me to the second ICE table on my left-hand side here. The second ICE table here, you will see that 1 mole for chlorine and then 0 mole for chlorine, then minus 0.7. Minus 0.7. Minus 0.7 represents the 70% use. And so under change in equilibrium to minus 0.7. While for oxygen, since I already known that here is minus 2x. So minus 2x equals to minus 0.7. So minus can cancel minus. Therefore, x will be 0.7 divided by 2, which is a 0.35. Therefore, if my x here for oxygen would be plus 0.35, because change in equilibrium is x, so that will be 0.35. It will be plus. But you cannot say 0.7 and 0.35 will be, no. It is based on the mole of the reactant and proton. There are 2 mole of the reactant and there's a mole. So 0.7 divided by 2, we have 0.35. Because 2 mole is 0.7, the mole will be 0.35, half of that. Okay, so we have established that. Then we can talk about now the equilibrium mole. Equilibrium mole, since 0.7 has minus 0.7 has been used, and then we know we add together 1 minus 2x, 1 minus 2, all right? 1 minus 2x. Okay, so we already know that our minus 2x is 0.7. So that will be 1 minus 0.7. And so we have 0.3 remaining. So that's 0.3 remaining for the mole of chlorine, while adding together here 0.35. So we have that. So total mole, our total mole would be 0.3 plus 0.35. 0.35, that will give me 0.65 as the total mole. Now, coming to the question, now we have to find Kp. So our Kp will be mole, the mole fraction of the product times the total pressure over because that one is just raised to power 1, and then from the formula there, from the formula given to us, power 1, and then we have for the reactant, it will be 0.3. Reactant is chlorine with 0.3 over 0.65, and total pressure squared. It is squared there. If that is done very well with a good calculator, we are going to have 2.53 times 10 to the minus 5. And talking about the unit, PA, Pascal to Pascal squared, how Pascal to minus 1. That is how to go about this one, and it's 3 marks. The mark distribution here is that this is M3. So this is your M3, and this is your M2, and the mole of the reactant and product is M1. Two of them will be M1. Very important. So you must work sometimes very hard to get 3 marks. So this is calculation. You have to get the fundamental knowledge of this calculation. And if you want us to solve more of this, kindly let me know when we meet in next class so that you can expound or explain more this type of calculation. Now we move on to the next question. Lucas reagent is a mixture of HCl and zinc chloride, primary, secondary, and tertiary, or can be distinguished by their reaction with Lucas reagent. Alcohol react with the HCl in Lucas reagent to form halogenoalkanes. The question is, zinc chloride acts as a homogeneous catalyst in this reaction. Explain the meaning of the term homogeneous. For in a simple language, it's a catalyst that exists in the same phase compared with the reactant. That will score you the mark. So this is your M1. Al2O3 is used as a catalyst in the hydration of alcohol. Alcohol, when they are dehydrated, you can use different catalysts. You can use concentrated phosphoric acid or concentrated sulfuric acid. You can also use Al2O3. So we have different catalysts. Here we have a solid form of the catalyst, which is Al2O3. State the effect of using Al2O3 as a catalyst in the dehydration of alcohol. Use the Boltzmann distribution in figure 2.1 to help explain your answer. Okay, we are stating the effect now. It lowers the activation energy of the reaction. So this is your M1. This is your M1, and they're asking us to use the Boltzmann distribution for molecular kinetic energy and catalyst to explain. Here, without a catalyst, we have EA1. EA1, so it's without a catalyst. EA1 without a catalyst. And so since that one, we have seen that one, only a small fraction of it, to the right-hand side with that color. The fractions that have the EA that can effectively collide and produce a product. So once you use an catalyst, you have another EA2, and that EA2 can be represented with a broken line. So a broken line here, this is the EA2 with broken line. The EA2 in diagram shows that the energy has been lowered further, making more molecules to have the EA required for effective collision. Okay, to make the reaction faster. So they are asking to use diagram. So M1 is lowers the energy, and then how many marks are there? The total mark there is 3 marks. So we've seen M1. Then the M2 will be this one without a catalyst, M2, and M3. This line that you have drawn, M3 will be this one, the broken line drawn, and the shaded portion of that broken line. That will give you the M3 for that reaction. P4O6 is a white solid that has a melting point of 24 degrees Celsius. Solid P4O6 reacts with water to form A3PO3. Deduce the type of structure and bonding shown by P4O6. I saw that you got that on your answer. It has a low temperature, means that it's a simple molecule. There's a simple molecular structure and with covalent bonding. Okay, that is that. Determine the oxidation number of P in H3PO3. Also got that one correctly. So we have your M1 here, it's correct. Then have M2 here, so correct. Here is M1. So you got a couple of answers. I'm going to post the answer, but this is the video for you to go through it and make necessary correction. For now, we are going to stop here. So when we meet on Thursday, we can explain further on or take part in many examples as possible. So I see you until then. Until now, I want to wish you Merry Christmas and enjoy yourself. God bless you.